So yesterday we were looking at the Fibonacci search method where we exploited the power of the Fibonacci sequence, okay, in eliminating one of the 2 points in the 2-point test at every iteration. So we solved this cylindrical solar water storage heater problem, and finally we got an uncertainty of about 0.173 meters. We reduced it from 3 meters, okay. We started the radius starting from 0.5 to 3.5 meters and finally came to something between 0.76 and 0.94 or something like that, right, 0.77 and 0.94 or something like that. So though theoretically the RR is supposed to be 1 by f of n, we were never able to reach it because the last iteration both the points were at the center and we are not able to proceed any further, okay. So we will have to revisit our reduction ratio, I mean whatever we arrived at. So what is the actual reduction ratio? Because if we take f of 8 is equal to 34 and we started dividing the interval as 21 by 34 and then 13 by 21, we were not able to do the 8th evaluation at all. 8th evaluation was at the center. It does not help us because we are not able to get 2 points because it reduces to half, okay. So okay, but we were able to do only 7 evaluations, correct. Therefore, so we have to revisit this, we have to pose the problem as n should have been correct. This is what we got. 1 by fn theoretically there is nothing wrong with that formula, but cannot be reached unless you do some small tricks. I mean you change that point slightly left of the center or something like that, but then it does not become the Fibonacci. The basic point is the last 2 evaluations you are not able to do because you hit the center. So now we will say that the RR is equal to f of n plus 1 by 2. So RR is basically I naught by In, right. So I say I want an accuracy of 0.18 meter. We could have started out with this problem as follows: minimize the surface area of the cylindrical storage water heater with an initial interval of uncertainty of 0.5 to 3.5 meter. I want to get a final uncertainty of 0.17 or 0.18 meters. So 3 divided by 0.18, reduction ratio is 17. If the reduction ratio is 17, f of n plus 1 must be equal to 34. So 34 corresponds to the 8th number in the Fibonacci series, therefore f of n, so therefore n should have been 7 and you will start with 7 and you will do 7 evaluations. Anyway 7 evaluations you do not have to worry about how many evaluations you are doing. Anyway, at the end of 7 evaluations it will come to a halt. This is the way you work out a problem, right. You have to work backwards from the final desired level of accuracy you need on your solution. Is that fine? So now we will go to yet another powerful method in our quest for developing efficient single variable searches. So thus far from whatever we have seen, so there are some basic cardinal principles, right. The 2 points must be close to the center of the interval. The 2 points must be close to the center of interval, and the 2 points must be equally spread from the on both sides of the interval. And common sense tells us that the 2 points must be at the same distance from the ends of the interval, because a priori you do not know whether the left hand side will be cut or the right hand side will be cut. Any disturbance to this, that is the distance from the left side is not equal to the distance from the right side, sometimes it may be advantageous, sometimes it may be terrible, okay. Therefore in all these methods including the Fibonacci method, it is at the same distance from both the ends, right. So the Fibonacci method actually obeys all this. Always we use a 2 point test, it is symmetrically placed about the center, it is symmetrically placed about the two ends, okay, and we get a good reduction every time. But the only thing is the Fibonacci, there are 2 or 3 disadvantages as far as the Fibonacci search method is concerned, basically because n is equal to 7 or n is equal to 8 is basically for trivial problems which you solve in the class. When you want to solve very complex optimization problems, 100 variable problem, when you desire a high level of accuracy, n may be 200, 300, 400, whatever. So you have to calculate and store the Fibonacci numbers first in your program, and you have to recall those Fibonacci numbers every time, okay. That is one thing. And the interval is not the same in the reduction in the interval of uncertainty is not the same in all the iterations, because 13 by 21 is different from 8 by 13 is different from 3 by 5 and so on. So can we think of some method which enjoys all the advantages of the Fibonacci search method, at the same time we are having the same ratio of we have the same interval reduction, that is when you go from I0 to I1, how much whatever be the percentage of reduction in the interval of uncertainty when you proceed from I0 to I1 is exactly the same as what you would get from I1 to I2 and I2 to I3 and so on. Can we come out with such a thing? Let us see. Can we try for a new search method? So to make the problem tractable, instead of 0.5 meter to 3.5 meter and A and B, I can have it as 0 to 1 just for demonstration. So I say that x equal to 0, x equal to 1 in appropriate units, meter, centimeter, kilometer, whatever, okay. I take 2 points, x1 and x2, okay, and I say that these are a distance of tau from both the ends. So x1 will be tau, x2 is equal to 1 minus tau, that is it. We are still talking about a unimodal function based on the 2 point test. One portion of the interval can be eliminated. Let us say the region to the left of x2 can be eliminated, okay. Let us say so what is my I0? I naught is 1, okay. What is I1 now? Good, I1 is tau. So we are starting from x2, right? We are starting from x2, okay. This is x equal to 1. Two points x3, x4. Sorry? Yeah, correct. Okay, 2 points x3 and x4. I want the what is our goal? What is our objective? Our objective is to come out with an algorithm such that if I1 is equal to tau into 1, I2 is equal to tau into I1, or it should be tau square into 1. We are getting that point? We are trying to seek such a, so this will be tau square, this will be tau square, correct? I do not know what the tau is, I am just trying to see if there is one tau. Now x3 equal to 1 minus tau plus tau square. Why is everybody blinking? What is x3? 1 minus tau plus tau square. x4 1 minus tau square. Nothing great so far. So we started out with 2 points x1 x2 but in the interval 0 to 1, and we are saying that first in the first iteration the percentage of reduction is tau, then we are saying that this percentage reduction has to be maintained. So the second iteration we take the 2 new points x3 and x4, but now we want to retain all the advantages of the Fibonacci search method. Therefore I want x1 to be x4. If x1 has to be equal to x4, so tau is equal to what is this 0.618. Yeah, what is root 5? 2.236, 2.23 minus 1, it is 0.618. Is this clear so far? Okay. Yeah. What is so great about 0.618? Check. That is why it is satisfying your property x1 is equal to x4. So 0.618 or 1.618 is called the golden ratio. Either this or this called the golden ratio, golden number. So if phi is your golden ratio, what is the property it satisfies? 1 by 1 plus phi is equal to phi. Again if you solve, phi square minus phi minus 1 equal to 0, phi is equal to 0.618. That is the power of the golden ratio. So now why instead of struggling with Fibonacci, every time you multiply 0.618, and 38.2% of the interval will be gone. That is a golden section search. Take 2 new points at a distance of 0.61 times I naught from both the ends. Next it will be 0.618 times I1 from both the ends. So you will get a very good reduction ratio. Now are there other properties which this fellow has? This phi itself, why this name phi itself? It was first used by some Greek guy, right? So he took the first 3 letters of his. Okay. So in fact if it is written like this by this is the golden ratio. Uppercase, lower case you write like this, that is also in golden ratio. So the ratio of of Egyptian pyramids is in the ratio of 0.618. There are also claims by Leonardo da Vinci and all that a beautiful face, the ratio of the height to the width of the face must be 0.618, and so there are so many other things about it. But the holy cross of the Christians is not in 1.618. Does anybody have a cross? No? I don't think it satisfies 1.618. I checked it once, so it has some I got it from some student. It's not, it doesn't appear to be, and the A4 size is also not 1.6, 297 by 210. What is the ratio? A4 size paper.
1.4.
1.4 is more aesthetic, man. There should be something. Everything is dry math, solving equation, minus b plus or minus. What is the use? Whatever is good to the eyes. 1.4. The A4 size is 1. Why should it be A4 size? Why can't we have like this? So for most people it is comfortable, it seems. Okay, that is not, unfortunately, it's golden ratio, that's silver ratio or something. So 1.4. Okay. So now what is the connection with the Fibonacci series? Please check this also. As you approach larger and larger numbers of the Fibonacci sequence, it reduces asymptotically to the limit 0.618. So all these are interconnected. So you want to enjoy all the benefits of the Fibonacci search, but you don't want to calculate and store the numbers, you don't want to have unequal intervals. So use the golden section search. Alright, fine. This is true. 21 by 34 itself is 0.618, right? What is 13 by 21? (21 by 34) huh? 6.1? Okay, 34 by 55. Okay, we will stop here. Okay. And we are having trouble when you reach that 1 by 2. That's where we struggle, right? The algorithm struggles. Fine. So now we will revisit the cylindrical solar water heater storage problem, but now with the golden ratio we can do it very fast. You don't have to remember the Fibonacci numbers. Okay. Now problem number
35.
And then hopefully we will give a decent burial to the cylindrical storage, because our quest for single variable searches ends here, and from the next class onwards we will do 2 variable search, and then we will start a new problem. Okay. Problem number 34, 35, what is it? and so perform 7
what is known as beating a dead horse.
Perform 7 functional evaluation, so that we so it is the same number as what we did for the Fibonacci search. So the problem reads like this: perform 7 function evaluation and report the final interval of uncertainty. Okay, so this is the problem. So A. So A equals 2 pi r squared plus 8 by r. Please start. I think the good news is most of these R1, R2, R3, R4 will be similar to what you got in yesterday's class. So you can really do the problem pretty fast. R1 is going to be, so R1 correct, 0.618 times 3. What is 3 is I naught. I naught is 3.5 meter minus 0.5 meter. $2.35. Yeah, yesterday we got 2.35. No, we use that 2.35. Yeah, if you don't like it, 2.34 you can use. What is the other one? 1.65.
1.646.
1.65.
Yeah.
Okay. If you have yesterday's notes, you already have A of R1 and A of R2. Okay. A of R1 is 31 point, is it? Correct, 38.1 meter square. A of R2 21.91. A of R1 is greater than A of R1 is greater than A of R2, and you are looking at minimization, so the region to the right of R1 can be eliminated. Correct? So I1 is correct. How much is the interval reducing?
1.61 times.
Interval is reducing by 38.2%. Okay, from 3 meters it became correct. So 61.8% of the original interval remains. Okay. Now R3 R4 R3 equal to how much is it, Deepak? 1.64 is it? So we have to, we can't use 1. We'll use the 1.65. What do you say, Samaj? Shall we use 1.65? As of now, you'll use towards the end. Some small problem will be there, that we can manage. Okay, R4, that will be new. Yeah, that will be new. Huh? Yesterday we got 1.20.
Yeah.
This is also 2067.
Yeah.
It's
Yesterday.
close, very close.
Yeah, then you can use the 1.20 value
1.08.
itself. You can use the 1.20 value itself. Doesn't matter. So A of R3 21.91. A of R4 I think it will be lower. 15 point? Fine. Region to the right of R3 can be eliminated. So how many evaluations are over now? No, how many times you evaluated the function? Not 4 times.
3 times.
3 times. We did only 3 times. The fourth one was buy 3 get 1 free. Correct? It's an offer. It's an offer. So the fourth one is an offer. Now we'll go to the next iteration. R equal to, it's not good. What is this now? R3? R3, no? I2. Green chalk. It's much faster than Fibonacci, it's much easier to work out, right? It's pretty rapid. Yeah, now you have to tell me. R5 equal to point
1.208.
R5 is point
1.201.
1.20. R6 okay. A R5 15.7. R6 also we have from yesterday's notes. 14 point? Okay. Again we are eliminating to the right, is it? Huh? Yeah. So be patient. I asked you to do 7 evaluations. We have completed 4. It has just taken 10 minutes. Not even taken 10 minutes. It has taken 8 minutes. So if I ask you to do 7 or 8 evaluations, I expect you to finish between 12 and 15 minutes. No. and not the same problem also. Anyway, now you can guess exhaustive search I will not ask, right. So it could be dichotomous Fibonacci golden section, just practice, that is it. So you have to bat on Monday, so you will have to, even if you know the algorithm, you should not make mistakes. By the way, it is open notes as before, so please come by 8:50, don't sorry 7:50, 8:50 everything is over, the game is over. So please come by 7:50 and don't get involved in what is known as a run around scheme. That is you don't bring the ID card, then you have to go and meet the HOD. That is called the run around scheme of the heat exchanger. So don't get involved in all that. Don't bring photocopied notes. Okay, bring your ID card. Calculators will not. These simple rules, if you follow the simple rules, you can write the quiz very peacefully. So get hold of yourself, organize yourself. You are not in the first year, you have done so many times, right. If you ensure that you are not indifferent, then you will do all this. Okay. So anyway, this my papers are all very computation intensive. So be ready to receive the paper by 7:58. Whenever they give, just take the paper and start working out. 50 minutes is not sufficient. Okay. If somebody has missed some class, don't bring photocopied notes, and then somebody invigilator this thing, and okay, please copy the notes today and tomorrow. That's a good way of learning the lessons also. If you don't have time to do that, at least copy the algorithm. Copy the algorithm, and you should know where the algorithm lies in your notebook. If you start searching, if you try to be like a great scientist and oh Fibonacci. The notes is just to suppose what is the 8th number or the 9th number, it is only for that. What is Fibonacci sequence? If you try to discover the method at 8 o'clock, it will not work. Okay, so now region to the right of R5 can be eliminated. R5 is what? 1.21. Okay, so R7 0.94, good. 7. We are reaching the end of our Fibonacci search, right? We all okay. A of R7. 1.3. Make it more than that. No, yeah. 14.12.
Yeah.
Actually, that is 14.06.
Okay, then we will say 14.06. Now we have to get 1.
14.12.
So AR7 is less than AR8 for a change. So the region to the left of R7 can be eliminated. No, the region to the left of R8, correct. R8 is what, 0.77? This is R5. Point 44. 44. Yeah, this is where we stopped in the Fibonacci method. Now you can keep on going in the golden section search. no R10 R10 R11. Yeah, now tell me R10 9 and 10, sorry. Yeah, R9 1.04, R10 is the same 0.94. Is everybody through with this? So, R10 A R10 already there. So, what is the story now? A R10 A, have we completed 7 now? Oh, we did not complete 7, okay. Therefore, region to the left of A10 is great, AR10, AR10 is less than, right, correct. Therefore, the region to the right of R9. R9 is what? One region to the right of R9, no? R9 is what is it? R8, 0.77 is it? It is pretty slow. No, I should not say that. So, I5 point. Yeah, I think we have come to the end now. .14. So, AR12 is less than, therefore, region to the right of R11 can be eliminated. Therefore, and the other one is 0.94, is it? The same thing what you get in Fibonacci, right? It should be the same, the reduction ratio will be the same, you did the same number of evaluations. Only thing, the advantage is you do not have to remember the Fibonacci number and 0.618 and fine. So, this is the story now, this is the final interval of uncertainty. What is RR? RR is RR where n is the number of evaluations, just check it. It will not be n because it will not be n because the first time we do 2, right, the first time we do 2, this therefore it has to be, what is this value for this? 17.91 is equal to 17.9. N is the number of evaluations. Okay, so we have learned quite a few powerful techniques for performing single variable searches. These are all only first order accurate in the sense that we do not exploit any information on the derivatives or the higher order derivatives, or we do not even look at the nature of the variation of the y between 2 points. We are just seeing whether numerically it is greater than or less than, that is all. Obviously optimization specialists and mathematicians would not have left it like this. There are other powerful methods which will exploit all this. Because of lack of time I cannot discuss on many of this, but at least one I would like to give you a sneak peek of how powerful we can get by employing some additional slightly superior or more advanced techniques to this problem. Let's stay with this R8 and R11. Let's see whether we can do something to improve this further. So A of R okay, suppose I want to expand f dash of x around x of I plus 1, I expand it as this perfectly legal to do it using the Taylor series expansion. I am not expanding f of x, I am expanding f dash of x around x of y. The next iteration f dash of x plus I is equal to f dash of xi plus f double dash into delta x plus higher order terms, and now the goal is to make f dash of x 0 because we are looking at an optimization problem, right. Therefore, if f dash of x is made 0, now you can see that x of I plus 1 minus x of I is equal to minus f dash of x I divided by f double dash of x of I. Therefore, x of I plus 1 is xi minus this is the Newton-Raphson method for an optimization problem. This is quite different from the Newton-Raphson method for the for the simulation where we have x of I plus 1 is equal to x of I minus f of x by f dash of x. Here we are having f dash of x divided by f double dash of x, because we are trying to make f dash of x stationary and not f of x stationary. Is it clear? Okay, so this is the Newton-Raphson method for optimization. So it is exploiting information on the first derivative, second derivative. So it is demonstrably superior. We will demonstrate it. It is far superior compared to the other search techniques. But what is a pain? First, it should be possible for you to evaluate f dash of x and f double dash of x. Suppose you are solving a CFD problem, or you are solving the vector Helmholtz equation, or you are trying to determine stress and all this. Getting the value of y is itself difficult. Outside of that, you want to get f dash, f double dash. So calculus is not the only route to solving optimization problems. This may look very attractive, but it is simply not possible to get the higher order derivatives when you are working with complicated optimization problems, where each function evaluation itself is so difficult. You may argue I can get all these derivatives numerically, all that is fine, but when golden section search and other things are available, or I will go for a neural network. If time permits, I will talk about neural network, right. So let us take this problem, we still have 5 minutes. So we will look at let us take R12. R12 should be what? Point
0.875.
0.86 or 8?
0.86.
0.86. Let us take R12 is 0.86. Let us apply the Newton-Raphson method. Can you give me the two values? I have already given the derivatives at 0.86. It will be 0, I am already there, I am home, but I will just want to demonstrate. Huh? Which is 0.8? No, you tell me the two values, Sampath, numerator and denominator. Abhishek, you have the values? You gave up? Huh? Yeah, give me the two values. One of you at least.
Numerator is minus 9.6 into 10 power minus.
Denominator is positive, I know that. Cupped, that is a change. 4.1 10 to the power of minus 4, which one? The ratio? No, tell me separately.
Minus 9.57.
That is correct? Minus 9.57
10 power minus 3.
divided by? Already you know that a dash of r has taken a very small value, therefore you have hit a dash of r is already becoming 0, therefore that is the optimum. So ri plus 1 is how much? 0.861 or what is it? Okay. So I have taught you what is called a hybrid optimization technique. You start with a search technique and find Newton-Raphson method is also a search technique, but towards the end you are using a search technique which exploits the power of the first derivative and the second derivative in order to narrow down the solution. There are other possible routes to this problem. You have 0.77 and 0.94. You have one more point, 0.86. Go ahead and fit a Lagrange interpolation formula between the three, or go ahead and have a Newton's divided difference formula. Y is equal to a naught plus a1 into x minus x naught plus a2 into x minus x naught into x minus x1. Get all a naught, a1, a2, a3 from these three values, and then get the derivative of that function with respect to 0 and make it stationary and find out where it becomes 0. So many possibilities are there. Okay, this is only if asked. If or you want to get a very sophisticated, you want to get a very narrow interval, then you can do this. The assumption behind this is when these points are sufficiently close, if you approximate it by a second order or second degree or third degree polynomial, not much error is incurred, but this cannot be done from 0.5 to 3.5 meters, or if you are searching from 1 meter to 200 meters, you can't take 3 points and put a parabola, it won't work. But when you sufficiently narrow down the interval and you are pretty sure that the interval is already very tight, then you can do all these tricks. So these are all higher order methods, because you are exploiting, you are looking at the first derivative, and in fact you are looking at even the second derivative. Okay, so this puts an end to our to a study of search techniques with single variable. In the next class we look at multivariable search technique, first unconstrained and then constrained.